Hello everyone and welcome back to another video. Apologies for not having posted for a while. It's been quite busy, the week before spring break, and also SAT stuff. But anyways, this is a math channel, not a vlog, so onto the math. The integral I was originally trying to do was this one right here, the integral from 0 to 1 of 1 over x squared minus x to the third, all to the 1/3. And I managed to get the right answer, but yet somehow through something, when I tried to make the video for it, something wasn't working with the complex numbers, because the complex numbers don't want to work on Tuesdays apparently. But anyways, the point there is that I was kind of struggling just using complex analysis because some fickle stuff there. Like I got the right answer, but just explaining it again worked once, didn't work the second time, which is kind of funny. But I found another way kind of in the meantime, just like, hey, we can kind of use the beta function here, can't we? So that's what this video is. And what we're going to be doing is actually generalizing it and then kind of going backwards to solve it, if that makes sense. So one of the reasons why you're able to do this using complex analysis is that this is just the same thing as this right here, right? X to the 2/3 times 1 minus x to the 1/3, and kind of the beauty of what this the beauty that's here is it lies in the fact that whenever we do our residues and stuff, we end up getting, if you apply the residue theorem here, you basically get like a negative 1/3 derivative of like this right here, of like 1 minus x to the negative 1/3. And that way, even though you have fractional derivatives, everything cancels out nicely and such and such and such. And that kind of got me thinking, actually, well, why does that work? And the reason basically lies in the fact that we have a number here and a number here, and that these just add up to 1. So if we just kind of call this A right here, and B, the reason why this works with the complex analysis, in the fractional derivatives at least, I believe, is really just that, well, it's A plus B must be equal to 1, because, 2/3 plus 1/3 is 1. And so, we can kind of generalize this, can't we now? We can just kind of say that this is equal to the integral from 0 to 1 of dx, but instead of x to the 2/3, we're just going to have an x to the a times a 1 minus actually, I can do it like fancy like this, the way Math 505 does it. Yes, okay. An x to like the a, and then like a 1 minus x to the b right here. But I mean, we can always just put x and a back in terms of b, and we'll be doing that shortly. But the main thing to note here is that this right here is really just essentially another form of the beta function. So this right here is really just equal to, you can just kind of look this up on the Wikipedia page, but we can just kind of put this in the general form of 0 to 1 of some t to the z. Wikipedia uses z1 for some reason, that's kind of weird, but it's like a z1, and then like t to the z1 minus 1 times 1 minus t minus t to the z2 minus 1, and then with respect to t, of course. And what we can kind of do is just kind of, well, we can just kind of say, oh, well, yes, z1 minus 1 is equal to a, and z2, goodness me, I can't write today. Z1 minus 1 is equal to a, and z1 minus 1 is equal to b, right? I mean, this basically is just saying, I mean, there's really not. Oh, sorry, negative b and negative b and negative a. Do pardon me. But what this basically means is that we can just kind of sub everything in. Just kind of sub everything in terms of this. So this basically means that since this is true, this is just beta of z1 comma z2. If we express z1 and z2 in terms of b and a, we can just express this in terms of the beta function, meaning that this, not conclusion, but to make some progress, this is just, our integral is just beta of 1 minus a, and then 1 minus b, and again, these are just interchangeable. Now, the interesting part about this is actually, if you kind of just go back to this definition right here, you'll know that this is true. So this is really just beta of 1 minus a, comma a, which is interesting. Meaning that if we actually put this in terms of the gamma function, this is just gamma of 1 minus a times gamma of a over what? Gamma of 1 minus a plus a, gamma of 1, which is just 1. Oh, I should write that, sure. Gamma 1, why not? And that is just 1. But we can simplify this even further by Euler's reflection identity, which is quite literally just this bit right here. So this right here is just nothing but pi over the sine of pi times a. Oops. And that's really just the value of this integral right here. This generalized version, at least, it's just pi divided by the sine of pi times a. Meaning that if we go back to our original integral right here, you'll notice that we factored out this. We factored out that x squared, and we got the 2/3 there, and that's what our a is. So if our a is just 2/3, we like for the specific example, we end up just getting pi over the sine of what, 2 pi over 3. And if you just kind of think back to the unit circle, the sine of 2 pi over 3 is just the square root of 3 over 2, meaning that this is just pi over the square root of 3 over 2, or put simply, simplified, it's just 2 pi over the square root of 3, which is the answer to our original integral here. So yeah, this wasn't like a very rigorous video, and hopefully I'll be able to get the complex analysis with the kind of dog bone contour or barbell contour, whatever you want, sorted out in the future, hopefully soon over break. But at any rate, here's kind of something in the meantime. So I hope you all enjoyed, and I'll see you all in the next one.